Good morning, all. Welcome to Kripa's Wireless Wisdom City, to my channel where we discuss about 4G, 5G technologies, all of the wireless technologies and beyonds. Hereby address technical director, product manager, uh, chief architects, system architect, and the solution architects, even the technical specialist who are desiring to understand the very much internal of the 3GPP equations and the deployment use cases. So let's celebrate the knowledge. Let's start the topic of the day. Today we'll be covering high-speed train use case. This is coming under layer one topic, fondly called HST by the most of the system use case owners. Indirectly, it showcases as a Doppler effect. I would go in the very much internals how the UV and velocity, how it had portrayed and as a Doppler effect to our frequency, transmission frequency. It is coming under the 3GPP specification 38.101-4, Annexe B3. The keywords connecting to this topic: HST, Doppler effect, fast fading, and slow fading. We would see that for a given speed, how the fast fading versus slow fading situation arises when the distance between your Z node B and your mobile changes. And yes, this question is very tricky. Basically, the core concept of how the 3GPP has arrived at the equation, so that we understand the internal details to implement in the product. Okay, so coming to the question, describe high-speed train use case from 3GPP, explain 3GPP equation for the Doppler shift. So this is my 3GPP snippet, which I have given, table number B3-1-1 under 38.101-4. So if you look at here, let's go through the parameters list that is governing the HST use cases. The DS, this is the distance between two base stations. If you look at your the base station, these are all the base stations that are mounted on your track. This is your track, relay track, which which mobile is, the person traveling, or the UE, the person traveling with the UE and the high speed track. And this is a base station. And DS, right? DS is the distance between the base stations. D mean, so this is your base station, and this is your track. This is the minimum distance. As I said, D mean is a distance, the minimum distance between your, at any point of time. What is the minimum distance possible is your direct vertical fall on the horizontal fall on the user. So this is your D mean. And then velocity v at which it is the U is moving, and FD is your Doppler frequency shift that you would experience. So we discuss about d mean, we discuss about velocity, and this is your Doppler shift. So HST 750, HST 972, 1000, and 1667. The nomenclature here is these are all hertz, 750 hertz of Doppler shift. So this is your 750 hertz of Doppler shift. This is a 972 hertz of Doppler shift, and this is your 1000 hertz, and similarly 1667 hertz of the Doppler shift that you are experiencing. All right. So this is what 3GPP says, that the Doppler shift that it experiences. So we'll go to the more details. So what is the Doppler shift? As we understood in our school time topics, this is, let's say a user who is traveling with a high-speed train is transmitting the signal at frequency f0. All right. And whenever it is moving and it is traveling at the velocity, let's say high speed velocity, and this is the velocity. Remember, this is the direction. I will talk about it more details. Remember, this is the direction, right? And but whereas my transmission G node B at somewhere here, so when it is moving at this speed, right? So the change in frequency, whatever the original frequency that you have transmitted, which is f0, the change in frequency is equal to your velocity divided by c. The c is your velocity of light, and f0 is your transmission frequency. So this, right, this is your delta Doppler shift that you would experience. In other words, if you had transmitted f0, you would experience f0 plus this extra delta frequency, right? So when you are moving towards the base station, you would see there is an increase in frequency, okay? So in a very simple word, f0 plus delta f, you will experience this delta f equation as we saw here, right? This is the delta f. And when it is moving away, right, if you can see in the waveform, it is stretched out. When the waveform is stretched out, what does it mean? It means my frequency has reduced. In this case, when the frequency had increased, right, it's f0 plus delta f, right? And in this case, if you same delta f, right, it is the same delta f, but my equation is f0 minus delta f, right? Minus delta f, because I am moving away. So this once from this point onwards, I am moving away, and till this point, I am moving towards the G naught B. So that is how the 3GPP has visualized that EV moving, traveling, let's say a user traveling inside the bullet train, and it is moving towards the base station. Then there is an increase in frequency. The perceived frequency received at the G naught B has increased, whereas when it is moving away, it has decreased. All right. So let's come to the next topic. So here I had given the, I have made an Excel set for this. It's a very basic equation. What is my Doppler shift as we saw in the previous slide? It is your original transmission frequency. This f we can consider as f0 compared to the previous slide. F0 into velocity by c. C is your velocity of light. Let's say first to begin with 24 gigahertz. This is our FR2 transmission. And if you transmit at that frequency and velocity, you're traveling at 300 kilometer per hour, then and the sub-carrier spacing that you are let's say operating at 120 kilohertz, the Doppler shift that you would experience is 6.6 kilohertz. All right. Similar way you can take for other FR1 candidates. Let's say you're transmitting, you are at 3.6 gigahertz of transmission, and you are going at 300 kilometer per hour, and the sub-carrier spacing is 30 kilohertz. Then you would experience 1 kilohertz of Doppler shift. Remember the sub-carrier spacing more to showcase that how much error you would experience with respect to the Doppler shift that you would see at the receiver. They directly doesn't contribute to your Doppler shift. Rather, the center frequency, the center frequency, it plays a critical role. You can see that for the given velocity, when 24 gigahertz is there, my Doppler shift is 6.6 kilohertz, whereas for 3.6 gigahertz of transmission, my Doppler shift is 1 kilohertz. All right, this is very simple equations. You can put in Excel set, and you can find out the numbers. All right. So, and on the right side of the slide, if you look at, yes, the train is moving. You can see that there is a positive frequency, right? This is your positive frequency shift, and there is a transition as it is moving towards, and it is going towards from positive frequency shift towards a negative frequency shift, right? This is the transition, and again it stays at negative. Again, it's a positive and negative. As you can see, this is the point where it reaches the center point here, right? This is your center point where you are right under the nose of G naught B. That is where the Doppler shift is 0, because I would connect to the next criticals of the 3GPP, where it will explain why it is 0. And when it is going away, it's again increasing, and it's becoming the highest number in the negative side. Okay. So we will come, you will appreciate it in the next slides where I will explain the details. This is the crux of the slide. Okay, pause here and go to the details. Try to really digest what is happening around here. So this is a single tap channel profile, high speed channel profile. This is your crux of the equations. As I explained, this FD, I think I had discussed. You can imagine this FD as your this one, right? The delta F. But there is another component coming up that is nothing but cos theta t. Remember when I didn't write cos theta, it is cos theta t. That means my angle, theta angle is changing with respect to time. Now, what is cos theta t here? If you look at here, this is your base station and this is your minimal point. And if you see here, the this is your ds by 2. Let's say that you are at time t0, taken an example. And if you take from here ds by 2 distance, and this is your d mean distance, somebody asks you what is my theta t, you can easily derive, right? This at this, let's say at this time t0, my let's say I am at the starting point, cos theta t0 is equal to ds by 2 divided by my diagonal. This is my height divided by my diagonal. That's pretty simple, cos theta t. But remember, this theta is function of time, right? So this is my initial conditions. That's why I didn't add up anything, any complicated, because this is this distance, right? This is ds by 2 as I begin. This is my t is equal to 0 point. U is at this point, all right? Next, let's go to the next one, right? Let's go to the cos theta t. This equation let's derive, okay? This is a little complicated. Do you notice this here? This is your 0th point, and u was moving at the velocity v, right? So if that is the case, in the tth time, how much distance it has moved? By vt. Okay, let me zoom a bit to see it. So you here clearly, it has u has moved by the point vt, right? So if the u has moved by point vt, then it is very clear that the cos theta t now. Now what would be my cos theta, the theta t, right? My theta t would be, I can take this, the if I take the theta t here, uh, cos theta t is equal to this divided by my diagonal, and this distance is how much? Because the origin distance between this and this was ds by 2, and vt is the distance I covered already. So ds by 2 minus vt is the distance, right? So ds by 2 minus vt divide by, I have to find the diagonal. How much is the diagonal? Because this is my height and this is my base, so you can put L, root of L square plus B square is equal to H square. So D means square plus your ds by D means square and plus your ds by minus by 2 minus Vt square. That is nothing but your diagonal value, right? So then what is cos theta? Cos theta is nothing but ds by 2 minus Vt divided by the diagonal, and that is what exactly is put up in your 3GPP equations, right? I hope no doubt up here. So in very simple principle, this was my starting point and I moved by the this distance, so that I have a reduction in distance towards the G node B, and I found my height, and I found my diagonal distance, and I found my cos theta, which is the function of time. You can see very clearly that cos theta, now you can appreciate this is v into t. That means this is very much function of time. All right. So I hope this is good. This is so far all good. I shall cover now these two equations from the 3GPP. Right. So I think this is what I was talking in details of the equations in the previous slide, and I had given a single slide so that you guys can understand in details. Next, let me go to the next slide for the second next another equation. You can see the another case where time is greater than ds by v, okay? And because remember time is 0 here, and this is where the ds by v point, right? ds and distance by velocity is equal to time, and this is less than equal to 2 ds by v. Let's say somewhere the 2 from with respect to this, with respect to time here, let's say somewhere 2 ds is coming up here, right? This is where, let's say, 2 ds is coming up here. All right, for that, this is the 3GPP equations they have given. Now we apply the same concepts. So if you look at Vt minus 1.5 ds, if you remember, this is my starting point. I am at here. So this is my total distance. This total distance is how much? So from here to here, it will be Vt. And the base station that is scattering is now this one. So Vt minus, this should be how much? This from 0 to here, this is my ds, and this is my ds by 2. So ds plus ds by 2 is equal to 1.5 ds. So the distance, real true distance, so that is to be covered for determining the cos theta t would be Vt minus 1.5 ds, right? This is what you can see, right? To find the cos theta t. This is, and then you know how to find the diagonal elements. How to find the diagonal elements? You found this distance. Now you have to find the diagonal elements. Diagonal elements is nothing but d mean square and Vt minus 1.5 ds square. So that's very much same way. Cos theta is equal to your base by your height, and by that you could find that your cos theta t is equal to 1 minus 1.5 ds plus Vt divided by root of d mean square and minus 1.5 ds plus Vt. All right. So this is very similar to this. I hope this is also clear. Let me take it to the final line of equations. If you look at more than 2 ds, once it is 0, ds by 2, ds point at your 2 ds, you just repeat the equations. Nothing you have to do. To repeat the equation, what you do in mathematics? Basically, t mod. If you take the t mod, it will fall naturally to the next base stations. It's basically you are restarting your equations, if you imagine that way. Okay, I have given the very clear cut distance and diagrams visualization of this. This is a very good technical equations which you would not find anywhere explained how the 3GPP had arrived. So with that, we thoroughly explain how the cos theta t, which is the function of time, how it has been derived, which is indirectly not only just a function of time, it's a function of time, velocity, and the distance between the base station ds, and the distance between base station and your UE, the minimum distance d mean. So with all that, we could find there are 3 set of equations, and we had successfully derived those equations. All right. So this is one of the MATLAB simulations which I had performed. If you look at, I just tried to perform for 750 hertz of velocity for a velocity of 300 kilometer per hour. You would appreciate here that the whenever it was initially, because you remember that as I told, it is fd cos theta t. This is what we have learned, right? This is what we have learned. So this theta t, which is function of time, if you look at whenever it is right under the base station, right? It is right under the base station, cos theta t would be how much? 90. Theta t is 90, cos theta t will be 0. That is why the Doppler experience when you are right under the nose of base stations would be 0. And it will be highest, right? That should be FD value, original value FD. It will be highest when it is at the ds distance, ds by 2 distance. And as you see, the cos theta t as keep on increasing from the to as it moves towards the base station, cos theta t is becoming 90. Even the similar equations you can see here. And this is my cos theta t. Let me zoom it to help you. So if you look at it, this is theta t, and as the time moves, right? So as the time is moving here, if you look at, this is the point. You can see that it is moving towards the base station, the theta is becoming 90. Okay, so and this, if you look at here, sorry, this is the 90 pin. I'm very sorry. This is right under the base station point. This is where it is 90. So this is where cos theta t, it is increasing from 0 all the way to 90, again from 90 all the way to the pi. This is how the cos theta t is behaving. In the similar way, it is fd cos theta t. If you take fd cos constant, so this would look like more of a cosine wave. The waveform would look like cosine wave, but remember cos theta is more of a function of time here. All right. So I have, in this example, I have taken to demonstrate a d mean. As you know, all of you know by now that d mean is the minimum distance between a base station and your mobile. Whenever d mean is 20 meter, right? And another case is d mean is 2 meter. If you look at whenever d mean is 2 meter, you could see that there is a very sharp fall in the frequency, right? It's very sharp fall, whereas this is bit smooth fall here. Here the fall is bit smooth. Here you can see, but here the fall is very sharp fall. You will notice. So so these are the parameters, the simulation use cases that we demonstrate to the the deployment, the product architects and the technology directors to show them that what would be my governing deployment. Let's say how far my base station should be from my track, and how much distance you should maintain between your base stations. So with that, I would say that we have covered the very much details and the 3GPP equations. We have successfully derived the equations given by the 3GPP and showcase that how the cost the Doppler shift, which is function of time, and there is a cosine component which is coming to the picture, and also we showcase the distance between G node B that is deployed along the track of the bullet train, how it impacts, and the minimum distance between G node B and the UE, how it impacts. So with that, I hope you had a great time understanding these details. Any questions you can please post on my channel. I would definitely try to answer you. Any objections to my video also, where you find some lacking also, please address, because it is we are here to celebrate knowledge. That is the mantra of whole YouTube channel. I thank you all for joining my session. Appreciate for your valuable time, and please subscribe if you enjoyed the video. Thank you so much. Bye bye.